Yep, it's another MS Paint video. This is a topic that I've wanted to cover for a while now. I had kind of forgotten about it until I was reminded recently after watching Eric's video about how to fix the GD Demonlist. And one of the things he proposes in the video is that the legacy list, instead of keeping all of the levels that have fallen off of the extended list, instead that page would be transformed into a ranking of all 500 some odd extreme demons in the game. Or I should say, the top 150 is already on the main and extended list, but 151 through 500 and whatever would all be ranked on the legacy list, not to, accept records or anything, but just as a way for players to get a sense of what, in terms of comparing easy extreme demons, which ones are easier or harder than others, that sort of thing. Which, as he admits in the video, would be quite a monumental task. It would take a lot of effort. There'd be a lot of effort going into that. A lot of controversy as well, I assume. I mean, there's already plenty of controversy, as is with the top 150. So I believe I've found a way to sort of streamline that process using a branch of mathematics called voting theory, which you may not be surprised to learn I'm quite enthusiastic about, being both a math nerd and a politics nerd. Although it's not just applicable to politics, you can use it for other things like ranking video game levels, as I'll do here, or sports tournaments, lots of other things. So if you have, we're ranking all 500 or whatever extreme demons. So if you have an election with 500 candidates, I should clarify for my American audience, so in civilized countries, they actually have more than two viable candidates with a realistic chance of winning, if you can believe it. You don't just have to choose whichever the less terrible candidate is in order to prevent the more terrible candidate from winning. You can actually vote for who you want and do so without helping a candidate that you really, really hate. Because instead of just you vote for your favorite candidate and then the candidate with the most favorite votes wins, which is a very bad way of doing things, that's called plurality voting. There are a number of other systems involving the ability to transfer your vote from one candidate to another. So I might vote for my favorite candidate and my second favorite and then my third favorite candidate all the way to my least favorite candidate. The system that's most often used is called instant runoff voting, where everyone ranks their candidates from the best to worst, and that you tally up the first place votes. The candidate with the least first place votes is eliminated, and then all of their votes are redistributed. You look at all the ballots that had that candidate as the first place candidate and say, okay, well, who was their second choice? You do that for all the ballots. You reallocate those ballots to whoever the second choice candidate was, and you repeat the process over and over. You look at the next least number of first place votes, you eliminate that candidate, and so on and so forth, until there's only one candidate remaining, at which point that candidate is declared the winner. This is a much better way of doing things because even if you vote for a candidate that's not very popular and they get eliminated pretty early on, your vote will get transferred to someone else and then someone else, and eventually, even if there's only two candidates that can win, your vote will eventually end up with whichever of those two candidates you prefer to the other, and so you're not actually helping the candidate that you hate the most. So that's a pretty good system. It does have a couple of flaws in it, so, I mean, it's way better than plurality voting, for sure. It's not a perfect system, though. The system I'm going to be describing in this video is a bit of an improvement on that. So, for one, instant runoff voting fails the Condorcet criterion, which states that if a candidate is preferred by a majority of voters to any other candidate, that candidate must win the election. So, if there exists some candidate to where if you compare them in a head-to-head matchup against any other candidate, a majority of voters will prefer the first candidate. So candidate A versus candidate B, more than 50% of voters want candidate A. Candidate A versus candidate C, more than 50% of voters prefer candidate A. Candidate A versus candidate D, more than 50% want A, right? If that's the case for all of A's possible one-on-one opponents, then it makes sense A should win the election, right? That's the Condorcet criterion. and unfortunately instant runoff voting fails that criterion. The system I'm going to be describing passes that criterion, actually. Another one is monotonicity, which means is it possible to help a candidate by ranking them lower on your ballot, or is it possible to hurt a candidate by ranking them higher? You don't want that to be possible. You don't want people trying to cheese the system like that. Instant runoff voting, unfortunately, fails that criterion, but this system passes it. In any case, it's still way better than plurality voting. So it's a really good... There are other systems where you can prevent similar candidates from like stealing votes from each other, right? So what I'm going to be describing in this video is called ranked pairs voting. It was developed in 1987 by Nicolaus Tiedemann, who is a professor at Virginia Tech, naturally. He developed a system, and in my opinion, it is the best known system for running elections and producing the fairest and most reasonable outcome. And so I'm going to give a brief demonstration of that method here. So let's suppose that we are ranking 4 geometry dash levels. I'm just going to choose a small number like 4 to demonstrate. Obviously, you can extrapolate this to any number of possible candidates, but let's go with 4 candidates. So what I'm going to do is, let's do this. So let's say we're going to rank Tartarus, Sonic Wave Infinity. I just looked these levels up. They're all right next to each other. Truefit, and the Golden. I chose some levels that are all right next to each other and that are somewhat iconic, right? And we are going to be representing these levels with colored dots. So Tartarus, being a hell-themed level, is going to get a red dot. Sonic Wave Infinity, being a blue 9 circles level, is going to get a blue dot. Truefit doesn't really have one main color, but it's more purple than anything else, really, so I'm going to give it purple. And then the Golden, despite its name, is actually green. Actually, no, I should use a different shade of green. I don't want to confuse any colorblind viewers here. The Golden, that's actually probably a more accurate color for the Golden anyway. So these are the 4 levels we're going to be comparing. And what we're going to do is every single voter is going to rank those 4 levels according to how they think the levels should be ranked, from hardest to easiest. And so let's suppose that we have, I just stole these numbers off of Wikipedia. Let's suppose we have a total of 27 voters that are choosing the order here. So let's suppose that 7 of those voters have ranked the levels in the following order. They say that Tartarus, red, is first. Sonic Wave Infinity, blue, should be second. The Golden, which is in the lime green, should be third. And Truefit should be fourth. That's how 7 of the voters voted. You had another 2 voters vote as follows. They say Tartarus is the hardest. Truefit is the second hardest. Sonic Wave Infinity is the third hardest. And the Golden is the fourth hardest. This will take a while to set up, I apologize. Another 4 voters rank Sonic Wave Infinity as the hardest. Perhaps these voters are just not very good at Wave. They've got Truefit second, they've got the Golden third, and they've got Tartarus fourth. Clean that up a little bit. There we go. We've got another 5 voters whose ballots are in the order Sonic Wave Infinity, the Golden, Tartarus, Truefit, you have another one voter that says, actually, I think True If It is the hardest, followed by Tartarus, Sonic Wave Infinity, and the Golden. And finally, you have 8 more voters. They turn in their ballots and they say, no, we think it should be True If It, and then the Golden, and then Tartarus, and Sonic Wave Infinity should be the easiest of these 4. So these are the ballots that have been turned in. So you have, that's 27 total, right? 7, 9, 13, 18, 19, 27. Yep, okay, we're good. So 27 total voters. This is what their ballots look like. This is not all possible combinations of 4 levels, but I'm not going to, yeah. You can assume that 0 voters voted, for yellow, or green, red, purple, blue. Any of the other combinations you don't see represented here, we can assume that there's 0 such voters. So anyway, what we're going to do next is now we're going to create a table, and we're going to look at the head-to-head matchup of every level against every other level. So I am going to put the winner on the left side and the loser across the top for every single color matchup. And here's how we're going to do that. So, you've got red, blue, purple, and green. Red, blue, purple, green. So for each square, we're going to look at how many voters said that the winning level was harder than the loser level. So for example, for this square right here, I don't know if you can see my cursor, this square here, we're going to say how many voters said that red was harder than blue, right? So these 7 voters all said that Tartarus is harder than Sonic Wave Infinity. They have red over blue. These 2 voters also have red over blue. These 4 voters do not. They have blue over red, so we're not counting them. These 5 also have blue over red, so they don't count. This 1 voter has red over blue. These 8 voters have red over blue. And so we have 7 plus 2 plus 1 plus 8, which is 18. 18 voters say, that's not a very good 8, that Tartarus is harder than Sonic Wave Infinity. How about this next square? How many voters say that Tartarus is harder than True If It? Let's see. These 7 voters think that red is harder than purple. Tartarus is harder than True If It. These 2 voters also think so. These 4 do not. They have purple ahead of red. These 5 voters do. They have red over purple. This one does not. These 8 do not. So we have 7 plus 2 plus 5, which is 14 voters think that red is harder than purple. How about red over yellow? How many voters have red over yellow? It looks like it's just these 7, these 2, not these 4, not these 5, and then this 1, and not these 8. So that's 10 voters who think that Tartarus is harder than the Golden. This square next, we're going to... Oh, by the way, the reason that this square here is not going to be filled in is because it doesn't make any sense to ask how many voters think that Tartarus is harder than Tartarus, right? So all of the squares along the diagonal we're not going to bother with. So how many voters think that Sonic Wave Infinity is harder than Tartarus? So how many think blue is harder than red? Not these 7, not these 2, just these 4 and these 5, it looks like, have blue ranked over red. So we can put a 9 here. Although I suppose, actually, we could have known that just by saying, well, there's 27 total voters, 18 of them have red over blue, so the other 9 must have blue over red, right? It has to equal 27 when you add them, because you have to have red over blue or blue over red. It's got to be one or the other. No ties allowed. Actually, in the same way, we can put a 13 here and a 17 here, just by subtracting all of these numbers from 27. Let's look at this square next. We have Sonic Wave Infinity over True If It. How many voters agree? These 7 have blue over purple. These 4 do as well, and these 5, so that is 16, I believe. Yes, 16 voters total have Sonic Wave Infinity over Trueifit, blue over purple, and correspondingly you have 11 voters in this box right there. Let's finish off this table. We've got blue over green. You have 7 plus 2 plus 4 plus 5 plus 1, not these 8. So that's going to be 19 voters think that Sonic Wave Infinity is harder than the golden. And then you've got, of course, 8 voters here. And then purple over green. I'm using yellow and green interchangeably. How many voters have purple over green? Just these 2 and these 4, this 1 and these 8. So that's 15 voters have purple over green, and that leaves 12. All my notes say green, that's why I'm confused. So you got then 12 in that cell. Okay, good. So you can see from this chart, between any matchup between 2 levels, which level more people think is harder in that head-to-head matchup. Now, one thing I am going to change, actually, is, and I calculated these percentages ahead of time. Did I? No, I did not. I am stupid. But what we might do is, instead of... Because this example is unique in that every single voter ranked every single level, but you might not necessarily want that. It may be that, for example, you only want someone to rank a level if they've beaten it, or if they have the level done in 2 connected runs, like 0 to 50 and 40 to 100, let's say. You don't want just any Joe Schmo giving their opinion on what the top levels should be, right? You want people to judge levels that they have a good handle on, that they know about, right? And so we might modify this example, if not every voter is voting for every level because they haven't played it or they haven't beaten it or whatever. We might express these numbers in terms of not the raw number of voters who chose one over the other, but the percent. So you would look at, for example, for this cell here, you'd say red over blue. Look at all of the voters who have ranked both red and blue on their ballot. Of those voters, what percent have red over blue? In this case, it's, 18 is exactly 2/3 of 27. So for this example, you'd have 66.7% or whatever in that box right there. I'm not going to go ahead and change all of these values just for that, but just keep in mind that that's what you would do if you have some incomplete ballots, is what it's called, where some voters leave off some of the levels from their ballot because they're not qualified to judge them, right? So, that is the basics of how this algorithm is set up. What we're going to do next is I'm going to move this all over here, and then I'm going to shrink this up. Well, we can... This works, I think. Yeah, that works. Okay, so what we're going to do now is I'm going to draw a bunch of dots to represent each level. Now, let's see here. The first thing we're going to do, I'm going to put this back down actually for just a second. We're going to say, okay, what is the biggest margin of victory that we see in this chart? Which number is the biggest? And it's this 19 here. Blue beat green by 19. They didn't beat them by 19. 19 people think that blue is harder than green. That is the biggest number you'll find in this chart. So that's the biggest margin of victory, so we want to preserve that. So what we're going to say is, let me just draw 2 dots here. We've got blue, and we've got lime green. And I will now draw an arrow from the winner to the loser, like this, to say that blue has defeated green. And we will now cross this off since we're done using this. So for sure we've locked in that Sonic Wave Infinity, which is blue, will be harder than the golden, which is green. So blue will be ranked above green for sure. Next highest level is this 18 right here. Red defeats blue. 18 people think that red is harder than blue. That is a higher margin than any other pair of levels in the chart. So let's go ahead and draw a red dot here. And go ahead and draw an arrow from red to blue, since red has defeated blue. Next number is 17, because that's the highest number in the chart, and it says that green has defeated red. So green over red is the next highest pair, so we'll draw an arrow from green to red. Now immediately you might notice that something is weird here. We're saying that red is harder than blue, blue is harder than yellow, and yellow is harder than red. That doesn't make any sense. You can't have that. You can't have all three of those be true at the same time. What is called a cycle. This contradicts itself. You have a cycle of arrows that all point around each other in a loop. We don't want that. So we are going to just ignore this number here, this 17. This is going to take a back seat. We've already filled in the 19 and the 18. Those take precedence here. So we're not going to draw that 17 arrow, because it would create... It's ridiculous to say that red is harder than blue, which is harder than yellow, which is harder than red. That doesn't work. Next number is 16. Blue over purple. So let's go ahead and draw our purple dot, actually. And we say that blue is harder than purple. Sonic Wave Infinity is harder than TrueIfit, so let's go ahead and draw that arrow in. Very cool. Next one is this number 15 here, so purple harder than yellow. So TrueIfit harder than the golden. We want to draw this arrow here. Is that allowed? That is allowed. This is not a contradiction, even though we do have a loop of arrows. They're not all pointing in like a cycle. We say that blue is harder than purple, purple is harder than yellow, and blue is harder than yellow. That just makes sense, right? So we're going to leave that. That's allowed. We've used up our 15. Next number is 14, red over purple, right here. So let's go ahead and draw that, red over purple. Is that allowed? Let's see, red over blue, blue over purple, red over purple. Yes, that's fine. We can draw that. It does not create a cycle. And cycles don't just have to be like in a loop of 3. It can be red is harder than blue, is harder than orange, is harder than pink, is harder than gray, is harder than purple, is harder than red. Like that's a ton of... I mean, it still creates a contradiction. It doesn't matter if it's a 3-long cycle or 7 or 20. If it creates a contradiction, we're not going to allow it. I should just mention that. Next number is 13, purple over red. So we want to draw this arrow. Well, clearly that's a contradiction. We can't have red over purple and purple over red. That doesn't make any sense at all. So this 13 is going to go. Actually, a lot of these are just going to be the polar opposite of the arrow we've already drawn. So 12 says yellow to purple. That's not allowed, so get rid of the 12. 11 says purple to blue. That's not allowed. We've got a 10, which is red over yellow. I believe that's allowed. I'm going to actually draw it around this way so it doesn't intersect the other arrows. Is that allowed? Well, yeah, I don't want it to be inside the circle for reasons I'll explain later. Let's see. Does that create any cycles? It does not look like it. No, that looks fine, so we're going to leave that. I mean, you don't have to just look at it. There are computer programs that can do this in the blink of an eye and see whether it's going to create any cycles or anything like that. 9 says blue over red. That's not allowed. Get rid of that. 8 says yellow over blue. That's not allowed. Get rid of that. And by the way, if there's any ties, like let's say that there's 2 levels that half the voters think that one is harder and half the voters think the other is harder, ties can just really be broken arbitrarily. You can choose any method you want to resolve ties. Anyway, so this is our final chart with all of the arrows drawn in. So let's go ahead and interpret what this means. So let's go ahead and set up our final ranking. Make these numbers a little smaller. Again, I'll explain why later. So it would make sense for the top level to be the level that has, or the color that has all of the arrows coming out of it and none going into it. And you can see that that's the case for red. Oops. For red here, it has arrows going out from red into blue, into pink, or into purple, and then into yellow. and no arrows going into it, which means that no level has defeated it. I mean, we would have drawn the yellow to red arrow, but that would have created a contradiction, so we ignored that. With this final graph, red is undefeated, so we say that red is the number 1 level. Tartarus is number 1 here. And after we've done that, we're going to delete red, and we're going to delete all of the arrows that are connected to red. So delete that, and then delete this. And now you look at, say, okay, which of the remaining levels has all of the arrows coming out of it and none coming into it? Which of those levels is that? Well, blue has 2 arrows coming out of it and none coming into it. I should mention there was an arrow coming into it from red, but we've deleted that arrow. We've already taken care of red. Red is the winner. We know that red beat blue, so we've gotten rid of that. So these arrows are gone. So now blue has no arrows going into it. All of its arrows are coming out of it. And so we rank blue second here. Now we get rid of blue. Get rid of all the arrows that are connected to blue. Took a bite out of that yellow as well. And now it's pretty easy from here on out. You say which level, or yeah, which one has the arrow coming out of it, and that's purple. That means purple is the winner. We're going to go ahead and get rid of purple and the arrow connecting to it. And then, of course, the last remaining color is yellow. So yellow is 4th. And so this is our final ranking of levels. We have Tartarus red, number 1. Sonic Wave Infinity blue, number 2. A Truefit purple, number 3. And the golden green, number 4. So this is their final ranking of levels. You can imagine that with 500 levels, it's going to be the same thing, except that it'd take much longer to run. Okay, so this is a brief description of the algorithm. In terms of how it would actually be implemented, there's a couple of weird wrinkles that we need to iron out here. So in terms of implementation for the real demon list, it wouldn't make much sense to, every time someone beats a level, to add their opinion on and then reshuffle the list, like just run this whole algorithm all the way over again and have to do this every time someone beats a level or has a new opinion on a level or whatever. So I think it would make sense to have in 7-day increments. So like every Saturday, for example, is you update all of the ballots or all of the opinions or whatever you want to call them, and then run the algorithm again. It'll print out its list of levels, and then you update the demon list to be that, right? So as more levels come in, they're kind of they're moved up and down on a weekly basis, just to prevent it from being like too chaotic. And at the beginning, it will be very chaotic with so few votes in. But as more votes come in and we get an idea of what sort of levels people think are harder and easier, it'll even out. It'll stabilize, right? In terms of what happens if a new extreme demon gets raided, or what happens if an insane demon gets promoted to extreme, what happens then? I think it would make sense to have 28 days, so about a month period, so 4 weeks, for people to beat that level, or if they've already beaten the level, to give their opinions on it and sort of insert it somewhere into their ballot. So they've already got their levels ranked from 1 to however many they've beaten. So they might say, okay, well, I would put, in my personal list, I would put this new level here, between 6 and 7, let's say, and so it kind of shifts all these down. And so everyone who's beaten it updates their ballots, and then at the end of the 28 days, you sort of run the algorithm again, and then print out the results, right? And so you would do this on just a regular basis. There was one other thing I meant to cover but forgot about. Hope it'll come to me. So yeah, that's my idea for how this could actually be implemented for the demon list. So you just up. Oh, I remember what I was going to talk about. Yeah. So let's say that you have another level get raided. Let's say there's only 4 levels here. Let's say a 5th level gets raided. What's a level? Oblivion just got raided. That's kind of a rainbow level. I don't know what color I'll use. Let's use gray for Oblivion. Let's just say. Let's suppose that all of these 27 voters who voted in this original election Let's say that they don't change their respective rankings at all, but let's say that some of them beat Oblivion and add it to their ballot somewhere. They insert it between wherever they think it should belong, and they don't touch anything else. So if they thought that Tartarus was harder than the Golden originally, then in their new ballot, Tartarus is still going to be harder than the Golden. They're not going to swap those levels around. The only thing they're changing is where this new level is placed. Everything else stays the same. Let's suppose that every voter does that. And then you run the algorithm again after 28 days, or however long it is, and see what the results are. Let's suppose that the results look something like this. Let's suppose that after the results are recalculated, let's say you've got Tartarus still at number 1. Let's say you've got Truefit at number 2. You've got Oblivion at number 3. You've got Sonic Wave Infinity at 4. And you've got the Golden at 5. You might notice something a little bit strange here, which is Oblivion has just been placed at 3, because that was sort of the average, well, not the average, but that's where it would belong if we run the algorithm again with these sort of updated ballots. But you might have noticed that purple and blue have switched places. How is it then, if we're saying that the voters did not change their ballots, the only thing they changed is they added gray somewhere, the respective order of everything else has remained the same, how is it then that purple has leapfrogged blue in this way when all of the voters that think that blue is harder than purple still think that blue is harder than purple, and all the other rankings are the same? How is that possible? This is a problem. This voting system fails what's called the independence of irrelevant alternatives criterion, which is quite the mouthful. It basically says blue and purple are irrelevant alternatives. They're not relevant to the addition of this new element, gray. We would think, at least we would hope, that they're independent of any changes that we would make to gray. Moving gray up and down in a bunch of ballots should not change the relative order of blue and purple, because they shouldn't affect each other, right? So how does this happen? Well, unfortunately, this is a bit of a problem. Can we fix it? The answer is yes and no. So the problem is something called Arrow's impossibility theorem. Now, Arrow's impossibility theorem, this was actually proven way earlier than Nicolaus Tiedemann developed this voting system. Voting theory has been a thing for a while. Arrow's impossibility theorem, which has a bit of a negative name, it concerns 3 properties that you would expect to be true of any voting system that's halfway decent, right? The first thing we want is something called, what is it called? It's called the majority criterion, which says if every single voter thinks that, let's say, Tartarus is harder than the Golden, every single voter has Tartarus ranked above the Golden on their ballots. Every single voter that has them both on their ballots somewhere has Tartarus above the Golden. Then it should be that in the final ranking, after the algorithm completes, Tartarus should rank higher than the Golden in the final ranking. It would not make any sense for every single voter to say, yes, Tartarus is harder than the Golden, but then in the final ranking, the Golden is harder than Tartarus. It's obviously a bizarre thing to happen. We don't want that sort of thing to happen. Number 2 is the independence of irrelevant alternatives criterion, which I will abbreviate with IIAC. This is what I discussed earlier with the whole, you don't want to insert or remove levels and have that change the relative order of other levels that you would think would be unaffected, right? That seems obvious. That seems intuitive that you should not have that, right? And then the number 3 criterion is no dictator. You don't want one single voter who just decides everything and whatever they say goes. The final ranking looks identical to their ballot. You don't want a dictator system. You want everyone's votes to be counted equally. Now, Errors and possibility theorem, and this has been proven, says that there is no voting system that satisfies all three. You can get 1 and 2, you can get 1 and 3, and you can get 2 and 3. You cannot have 1, 2, and 3 all at the same time. There is no voting system that satisfies all three of these criteria all the time, unfortunately for us. And so one of these has got to go. We definitely want to keep this no dictator clause here. We want everyone's votes to count equally. And of the remaining two criteria, the majority criterion is seen as the more intuitive one. It just makes sense. We can't have every single person vote for one level over another, but then it's ranked below that level in the final ranking. That doesn't make any sense, right? So we have to do away with one, and we generally choose the independence of irrelevant alternatives criterion to get rid of. And so this little quirk, it can happen from time to time. It's rare, but it happens. And it's just, there's no perfect voting system, at least no voting system involving ranking candidates. There's no voting system that satisfies all of these. It's just how close to perfect can we get? And I personally think that ranked pairs voting is the closest to perfect that we're ever going to get. Maybe someone eventually will come up with a better system. This is the best I've found so far. But you'll never get a system that satisfies all of these. So anyway, that's about all I wanted to talk about. I hope you enjoyed this video. That's about all it for today, I suppose. Bye.